Welcome back. So now that we have a way to quantify the distance between the density functions or distributions, we are good to go. We will go back to our recipe, right. So let us go back to our machine learning recipe. Now given okay, for now, see, when I am formulating this the general solution for the ML problem, I will assume that we are given a particular random variable from a distribution and a lot of samples from it, or I can make an idea assumption and say that I have n random variables, one realization of each, and we have n of them which are identically distributed, independent and identically distributed. Let us stick to this view, okay. Let us, because the IID assumption is made throughout, let us stick to this view that we are given n random variables, one sample of each, all of which are independent statistically and identically distributed, okay. Now this methodology that I am going to talk about right now is applicable irrespective of the kind of data that you see, in the sense that it can be a supervised problem, it can be an unsupervised problem, or so on, right, which means that you can have label, you can't have label, and this methodology is applicable to problems where you are estimating marginals, or if you are estimating the joint distribution, if you are estimating the conditional, it does not matter, okay. That is why I will make it generalized in the sense that suppose we are given, suppose we have n samples, so draw an IID. So let us say that we have D, which is, I use another notation here, V1, V2, V3 up to Vn, and this is drawn IID from a distribution. I will write the density PV. So note that this V can be Px, Pxy, Px given y, Py given x, anything. So it depends upon what the underlying problem is. The treatment now will be general, okay. Now the goal is to estimate PV given D. This is our goal. Now we know the recipe. Assume P theta, which can be evaluated at V as, see, this V is a dummy variable, by the way, P theta as V as the model density, and compute KL divergence now between PV and P theta, okay. By assuming that we are dealing with continuous random variables, this is given by the integral of PV log divided by P theta evaluated at V, and you have dV here, and this is over the space that these random variables are defined. Let us assume that these all Vi's are in some d-dimensional real space, okay. That is the most general observation assumption that we made. This is what it is, right. Now what are we interested in? So remember the recipe again. So we want our theta star, or the optimal parameters, to be the one that minimizes the KL divergence between and P theta, correct. So this optimization is over theta, and you let us open this term out, and we have this integral PV log PV the second term is minus integral PV log P theta So integral is a linear operator, and I can open the log and write this as push the integral after the negative sign. So note that this first term, right, this term can be completely ignored. Why? This is independent of theta. Theta is the optimization variable, and the first term is independent of that theta, which is the optimization variable. Now how do you interpret this? I am saying that this is the entropy of data, and I can do nothing about it because data is given to me. See, if I have to minimize the divergence or the divergence metric between PV and P theta, the only thing that I can play with is P theta, not PV, because that's entropy of data and I have no control over it. So I can just knock that term off. Okay. Now this will be, I want to minimize the negative of the integral PV log P theta P dV. This is the optimization problem that I want to solve now. Okay. Now remember, in the first class somebody asked a question that aren't we begging the problem here, because we started the entire process by saying that we don't know PV, right? Now when we don't know PV, what's the way to compute this integral? Two things. The first thing is this integral is intractable in RD, it's in very high dimensions, it's very hard to compute. Other thing is that we don't even know what PV is. That's the whole problem that we are trying to solve. So how do we solve this problem? We use statistics. So we can write this as argmin. This is the negative of, what's this integral? This integral is expectation of correct. By definition, this integral is nothing but the expectation of log p theta with respect to PV. Okay. Now again, can we compute this expectation? No, we can't. But here comes the biggest twist in the tale, that statisticians tell us that expectations can be approximated using samples. So if you want to compute the expectation of a particular function with respect to a distribution and all that you have are samples from the distribution, then you can approximate that expectation using something, something that is computable. And there is a theorem that guarantees you that if you have large amount of samples, then this estimate that you have actually converges to the true expectation in probability. What's this theorem? Law of large numbers. So let's invoke that. Okay. So if we invoke the law of large numbers, you tell me which one. Weak law of large numbers. From the law of large numbers, we have expectation of log of p theta v with respect to PV can be approximated by, what's the estimator? What is the estimator that would estimate the expectation? It's the sample mean. Okay. So sample mean is given by 1 over n log of p theta of vi, where vi is sampled IID from PV. Only if this happens, law of large number works. So you have to ensure that all the samples that you have are drawn IID from a particular distribution, right? So now can we compute this quantity now? We can, because we know what p theta of vi is, because that's what we have defined, and we have samples from PV. That's it. So now law of large number says that this particular estimator converges to the true expectation as now you know why AI works only with terabytes of data. It's law of large numbers. What you are actually doing is trying to approximate an estimate, an expectation using sample average. And statistics tells us that that only works if you have lot of samples, right? So what is the infinity that is known to human beings? The entire internet. Train your models on the entire internet. That's the story. This existed centuries before. What did not exist is that we could not traverse this arrow, right? So this reminds me of a story, right? In a class of mathematics, it was being told that there are infinite numbers between these two, right? And a student came and did this and said, I just crossed infinity. Right? Anyway, right? So what are we doing is that by considering a large amount of samples, we are approximating the expectation using sample averages. Now our optimization problem boils down to the following. So we want to seek the minimizer of the negative of where Vi is sampled IID from PV. This became our estimator. But in fact, you'll be surprised to know that even ChatGPT is trained using the same equation. This is exactly what is done. So now how is the optimization problem solved and what p theta is being used is different. Okay. Now this is what I call as the minimal KL divergence estimator. Makes sense, right? Because all we are doing is just, if you trace back what we did, started from the definition of KL divergence, right? The estimator that we have gotten for the parameters theta is the one that minimizes the KL divergence between the true distribution and the model distribution.
What do the indices K and L stand for?
Come again?
The indices K and L, what do they stand for?
Oh, I thought I mentioned. They are the names. Kullback and Leibler, two people. Okay, KL divergence. In fact, the generalized version of it is what is called as an F divergence, and KL divergence is one member of that large family. So KL divergence has its problems. It's not the best divergence to be used. Surprisingly, this is what is being used even today, and it sort of empirically works. Okay, so this is the minimal KL divergence estimator. Any questions so far?
Why did we use PV in the first in that equation?
Which one?
Yeah, that optimization problem. Why PV is first? Like any reason why?
Oh, here is it. Okay, so the question is why are we considering KL between PV and P theta and not P theta and PV? So typically in literature, no, this is called as forward KL. The term that you refer to is called the reverse KL. Okay, now if you take reverse KL, you will have a term that you cannot compute. You can see that, no, because there will be a P theta log PV term. We can't do anything about it. That's why we use the forward KL.
Mentioned that as n tends to infinity, that's that. So, but there I had a doubt. Why exactly is it not tending PV only? Whether you wrote P theta only, like
No, this is the expectation, right? This is the, see, okay. Um, Suppose there is a random variable. This goes to the foundations of probability theory. Suppose there exists a random variable. Okay, maybe I'll write it here. Mm. So look at this. There is a law called the law of unconscious statistician, or LOTUS. It is abbreviated as. Now suppose x is a random variable and f of x is a function of a random variable. So typically, or not typically, right, always the function of a random variable will have a different distribution compared to the original random variable. Now if I were to talk about the expectation of the function of the random variable, it's actually equal to the expectation of that new random variable with respect to the distribution of that new random variable. However, it can be shown that expectation of a function of a random variable with respect to its distribution is equal to the expectation of the function of the random variable with respect to the original random variable. This is lotus. It can be proved. I think it should have been done in STOMA or your probability theory classes, right? It's a okay. So what I am saying is show this result. Prove this. We'll fix that in next class. Okay, I told them. Maybe try to just push it a little or something. Okay, that is what it is. Yeah. Therefore, see, if you look at, if you consider that, then the expectation that we are trying to estimate is the expectation of this function of the random variable v. So this is that f of x that I wrote. So log of p theta of v is a function of the random variable v. So we are looking to estimate the expectation of function of a random variable with respect to the underlying distribution of the random variable, and we look at the sample averages. And law of large numbers tells you that the sample average will converge to the true expectation as n tends to infinity. Okay. Anything else? Okay. Now this is what I call as the minimal DKL estimator, but we also know that that I can write this as the max or theta of this particular function, correct? Because okay, now I'll introduce some nomenclatures. Remember I told you that if p theta is the model distribution that we have assumed over the true data, if you evaluate that at a particular point, I gave a name for this. If you evaluate the density function at a point, it is called the likelihood. Density functions being evaluated at a point is called likelihood. Okay. Now what is this? We are trying to find an estimator theta that would maximize the likelihood of all data points under the model. That is one other interpretation of this, and that is why this estimator is also called the maximum likelihood estimator. See, I can do the entire math in a different way. So what I will say that is that p theta of vi, okay, is the likelihood of vi under p theta. So what I want to do is to find a theta that would maximize the likelihood for the entire data set. This is for one data point. If I have to do it for the entire data set, what should I have to do? I will have to consider the joint distribution with respect to all the random variables that we have, and I have n of them. See, our interpretation is that our data set has n random variables which are all IID, correct? If I have to consider the joint distribution between n random variables that are IID, how do I do that? Product, right? So I'll the total joint likelihood of data, let me write that. The joint likelihood of the data, let me call that as L of D, is given by the product of all the distributions, right? Correct? Because they are IID. Okay. Now what do I need? This is a function of theta, of course. I need to maximize the likelihood of this, joint likelihood of data. Now I don't like products, so I'll go through, I'll make this go through a monotonic function, and log is one such thing. So what I'll do is that maximizing this is equivalent to maximizing the log of the likelihood of this. If I do that, then this will get converted into a sum. Okay. Then I seek theta star as the one that would maximize a scaled version of this. And people call this the maximum likelihood estimator. I am not a big fan of this, because why should you maximize the likelihood? To me, this estimator is the one that minimizes scale divergence. Mathematically, they are exactly the same thing, right? The one that maximizes the likelihood over the data is the one that minimizes the KL divergence between the true distribution and the model distribution. I would like to see that as the minimal KL divergence estimator, but I will call it as maximum likelihood estimator to ensure that I am following the convention.
Both are the same. This interpretation.
Exactly the same, no? That's why I wrote the math as well. But remember that all we are doing is minimizing the KL divergence between the model distribution and the true distribution, even when we maximize the so called likelihood. Okay?
So because of this law of large numbers, right? Assumption that
IID assumption is always made, and law of large numbers tells you that this is a good minimizer, this is a good estimator for the minimizer. That's it. See, the hand wavy explanation that people give is the following, right? What is p theta of v? P theta of v is the likelihood of obtaining v under theta. So what do we need? We need a model that would maximize the likelihood of obtaining this particular data set, and that is why we maximize the likelihood of this particular data set under the model distribution, and we seek the parameter in such a way that this would maximize it. So that's the hand wavy explanation that is given. Why should this be a good estimator and so on is a different question altogether, but I like to see that as the one that minimizes the distributional divergence between the true and the model distribution. Okay. Okay. Now one question that remains is any questions so far? Okay. See one, yeah.
Earlier we looked at the entire entropy thing is that the less likely an event is, the more information it gives us. So if we have a data set which is very less likely, and if we maximize the likelihood, it should give us a better, like it will end up giving us a worse model for the entire thing. But as per entropy, it gives us more information.
Okay, I'll sort of answer your question, but I'll make a comment with your permission. This is precisely why I don't want to see this as maximum likelihood estimator, because there's no mathematically grounded interpretation to what is being done. So to your question, see, look at what likelihood are we maximizing? We are maximizing the likelihood of seeing the data computed under the model distribution, that we want to maximize. Understand? So given that I am treating my data coming from the model distribution, give me that model distribution which would maximize the entropy, which would maximize the likelihood, not entropy. Okay, yeah, but again, as I said, seeing this as maximizing the likelihood is not something that I am a fan of. I want to see this as the one that minimizes the KL divergence. Okay. So wherever you see this maximum likelihood estimator, remember that it's the minimal KL divergence estimator. Okay, we will stop here and continue in the next lecture.